Hey everyone, it's Ken. This is a special video. This is when we get to do the definition of the definite integral. It's kind of a special place in the first semester calculus course. And so what this is intuitively is it's the signed area. So you take a function defined on an interval. Part of the function will be bigger than or equal to 0. Part of the function will be less than or equal to 0. So the part that's bigger than or equal to 0, you take the area under the function above the curve. You then subtract the area below the x-axis and above the curve for the parts that are less than 0. And that's called the signed area. The definite integral is actually the definition of area or signed area. And with that in mind, this definition that I'm about to write down will make pretty good sense. So actually, let's just dive right into it. So the definite integral from a to b, you start with a function y equals f of x. You want to integrate this function from a to b. And I'm going to write dx here. This is not multiplication. It's just the whole thing is part of the notation. And so this is supposed to be the signed area of f of x from a to b. And what this is, well, let's think about it organically. So you start with an approximation. Start with any approximation you want. For instance, a Riemann sum. So pick any partition of the interval from a to b. Choose any collection of points, one for each subinterval. And now take the limit as the mesh of the partition goes to 0. Well, that may be conceptually hard to understand at the beginning, so let me say a few words about that. What this means is a couple of things. So what I'm asserting here in this definition is that if you take any sequence of partitions, and then for each partition take any collection of sample points, then so long as the largest width, the largest delta xi, so long as the largest delta xi is heading towards 0 in your sequence of approximations of partitions, then if it's true that the Riemann sums approach a single fixed number, then we call that single fixed number the integral from a to b, the signed area. So to even break this down a little bit further, this definition is very general. I could specialize it. So for example, I could just choose, say, right-hand endpoints. So say that I did that. My Riemann sum with right-hand endpoints, I've got a formula for it. It's just f of x I goes from 1 to n times delta xi. And then the limit as this width goes to 0, that's the same thing as saying the limit as delta xi goes to 0. But for right-hand endpoints, delta xi is nothing but b minus a over n. So as n goes to infinity, as the number of rectangles gets larger and larger and larger, then certainly delta xi is going to go to 0. So I could even come back here and rewrite this whole thing as nothing but the limit as n goes to infinity of this sum f of x I goes from 1 to n times delta x. And this is maybe like more intuitive or easier to understand. So there's lots and lots of partitions and sample points you pick, or you can pick, but just so long as the mesh is going to 0, if they all go to the same value, then that's the integral. But if you know that they all go to the same value, then you will be able to calculate it with left-hand endpoints or right-hand endpoints, with this formula. That's why I actually need to use this to define the integral and not like right-hand endpoints. So what I mean by that is, say that I defined integration by just limit of right-hand approximations. I could find a function where all the right-hand approximations converged and gave you an answer, but maybe the left-hand approximations did not converge and didn't give you an answer. And then we'd be asking ourselves what's so special about right-hand approximations like versus left-hand approximations or whatever. So the way you solve that is you say, well, if one of the approximations sort of doesn't work to give you an answer, if one of those approximations isn't good, then you just say that function isn't integrable. You just say that function has no area in a way that it can be defined. So every approximation has to work. Every Riemann sum has to be close to a single number, which is going to be that signed area. And you take the limit and it'll give you the integral. But if that's true, then you'll be able to calculate it by just using limits of right-hand endpoints or limits of left-hand endpoints, what have you. So that's the definition of the integral. And I'll actually give you an illustration. So this is, I've been saying it, this is the definition of signed area. And I want to give you an illustration to show you what I mean. So let's look at the function sine of x, and I'm going to take x goes from 0 to 3 pi over 2, and I'm going to show you the right-hand approximation with 100 rectangles. There it is. And already you can see that it's not literally equal to the area on the upper part minus the area on the lower part, the red part. But you can see it's pretty close because it's just the approximation. I haven't taken the limit yet. So that's with n equals to 100. So you can imagine as n goes to infinity, you're straight up going to get the signed area, namely the green part minus the red part. So that's your intuition for what the integral actually is.